So you can use your calculator to help you do these, and it'll be really quick. If you graph them and then hit Control T, remember, so here's your equations right here. Okay, hit Control T. It'll give you all the information you need for down here. Okay, so you may not need the whole 5 minutes that I'm giving you, but don't be wasting the 5 minutes either.
Yeah, a little bit. Did you know that's good? Yours?
So time's up on this front part here. So if you had the graphing calculator graph it for you and then hit Control T, right? Then hit Control and the T button, right? Then it will give you the table down here. So 2 times -2 is -4. Okay? 2 times -1 is -2. 2 times 0 is what?
0.
2 times 0 is 0.
-2.
Okay? And then +2 and +4. Okay? So if we graph these, we get -2, -4, -1, -2, 0, 0, 1, 2, and 2, 4, right? So here we go. We got a line here. So what kind of function is that?
Linear.
It's a linear function. Right? It's a linear function. So on this next one, if I graph -2 times, or it's not -2, sorry. What it is, -2 to the power of 2 times 2 out front here. So -2 squared is 4, right? Because -2 times -2, it's not negative anymore, it's +4, times 2 gives me 8. And if I did -1 squared, -1 times -1 is still 1, +1, times 2 is 2. So we got 0, then we would have 2, then we would have 8 again. Okay? So if I graphed those coordinates, okay, I don't have an 8 all the way up here, but I can estimate where that one might be, right, way up here. Oh, come on. Thank you.
Is all we doing today is notes?
Yeah. Nope. We should have a little bit of time at the end of class if we get going through this.
Just do more negatives?
Nope. Because you have -2 squared, and -2 times -2 is +4 times 2 is 8. So then we have, so -2 and 8, -1 and +2, 0, 0, 1 and +2, and 2 and +8. So when you connect all of your dots, you get this parabola, this U-shaped graph. Do you guys remember what kind of function that is?
I got it. Exponential.
Not exponential.
Ooh, a quadrant.
It's quadratic. So this one is, quadratic. Remember I told you at the beginning of the year, Q always needs a U, right? So the function that's Q, quadratic, is always U-shaped.
Yes.
So the last one is 2 to the power of -2. What do you get when you raise 2 to the power of -2?
Yeah, Isn't it
It's
oh, you're talking about the graph. Oh, 1/4.
The table, it's 1/4.
1/4.
It's 1/4. Remember that negative just means you're going to flip it and make it positive. So the power raised to the -2 is 1/2 to the +2, which is 4. So 1/4. And then the next one would be 1/2. Then we got 1, 2, and 4. Thank you. So if I graph this one at -2, I'm going to have a point just above the line there somewhere. And then halfway at the -1, 1 at the 0, 2 at the 1, 4 at the 2. So my line goes like this. Make sure it goes up more. And going this way, it kind of levels out. So what kind of a function is this one?
Exponential.
Exponential. So the question here is, how do you tell? Right? By what they look like. So the linear one makes a line, right? The quadratic one is a parabola shaped. And the exponential one is a curve. Okay. The other way to tell is if you have a table and you don't want to graph it, but you're given a table, how does it change on my y side? So I'm going up by 1 over here on my x side. So what happens to go from -4 to -2?
It goes down, drive up.
I added 2 from -2 to 0.
+2.
+2 from 0 to 2.
+2.
From 2 to 4.
+2.
Okay, so linear equations are always adding or subtracting. Okay, so the difference is that when you look at the table, the pattern is always adding or subtracting. For an exponential, okay, what pattern do you see over here?
There you go. It's like
It's going up.
It is going up by what?
By 2.
It's multiplying by 2 this time, right? Whereas it's adding by 2 for the linear, but for the exponential, it's multiplication. So exponential functions are multiplying or dividing, okay? We really tend to think of them in terms of multiplication. We just would use a fraction instead of dividing. So with quadratic, there is a pattern on the table. I mean, you can tell it goes down, right? And then it goes up. Okay, so these numbers go down and then these numbers start going up, so they flip around. But if we were to look at the pattern, how did it change going from 8 to 2?
It's going down.
Down 6. From 2 to 0?
-2.
-2. From 0 to 2? +2. From 2 to 8? Okay, and then that's considered the first difference. But if I go to what is called the second difference, okay, from -6 to -2, what do I do?
+4.
Add 4 plus 4. So -2 to +2?
+4.
And 2 to 6?
+4.
Okay, so for a quadratic equation, the pattern happens in the second difference, and it's an addition pattern, but it's in the second difference. Whereas with a linear pattern, it's in the first difference. Okay, so that's how from a table you can tell which type of function it is without having to graph it first. So down here at the bottom, okay. Oh man, I erased my thing that I had there. I already had that typed out and I erased it. Anyway, okay. So an exponential function is a function where there it is. Whose independent variable got too many. Its independent variable is an exponent. Okay. So exponential function is a function whose independent variable is the exponent. So that's just saying that the number that you're substituting in for is the exponent of your function. So now let's fill in this table down here. Okay. We've got okay, so 3 to the power of x. So 3 to the negative 2 would mean I'm doing 1 over 3 squared, right? So what's 3 squared?
9.
9. So 1 over 9. And then this would be 1 over 3 to the power of 1, so 1/3. Anything to the power of 0 is 1. Then we've got 3 and 9. So if I graph these on the graph here, negative 2, it's barely going to be above the line. Then 1/3 is a little bit taller. 0 is at 1. 1 is at 3. 2 is at 9. Can't draw a curve very good on this thing. Anyway, okay. Okay, so there's my exponential function. Not pretty on my tablet here, but there it is. So we have a new word down here at the bottom that we haven't seen before. The asymptote. Okay, so horizontal asymptote is the line, the invisible line that the graph never crosses. So in this case, my horizontal asymptote is right here. Okay, and it's usually drawn with a dotted line there. What equation would I use to represent that line? Y equals or x equals?
Y equals.
Y equals. Y equals what?
Like 1.
At this line right here, what does y equal on the x-axis? On the x-axis, what does y equal? 0.
0.
So y equals 0 is my asymptote. Okay? It's the line. Okay? The asymptote is the line that the function gets closer to, but never touches or crosses, you can think of. Ran out of room at the bottom. Okay? It never touches or crosses that line. If I put 3, so if I went backwards this way and I did 3 to the power of negative 5, what fraction would I get?
You said what?
I did 3 to the power of negative 5 in my calculator.
You said 1/5?
1 over 243. Does that equal 0?
No.
No, but it's a pretty small number, right? So that is what happens. If you keep taking something and halving it or dividing it by 3, then it's going to get smaller and smaller and smaller. But theoretically, even if it's a nanoparticle, you can still half it again and make it even smaller, right? So what happens in an exponential function is it never reaches this line that we call the asymptote, okay? So I kind of give a funny analogy to help you remember what I'm talking about when I say asymptote, okay? Think of what the beginning of that word sounds like, right?
Yeah.
Okay. So if you think about that crack, okay, does one butt cheek ever become the other butt cheek?
I mean, they're kind of the same.
Okay. But do they actually ever become one?
No.
No. Does one ever actually cross the other one?
No.
No. So this right here is like your butt crack. This is going to get closer and closer and closer. This is one cheek. This is one cheek of your butt, and it's going to get closer and closer and closer and closer, but it's never going to cross that line. Okay? So, like I said, it's just a funny way to help you remember what it is, because vocabulary is everything sometimes on the STAR test, right? So if you don't remember what a vocabulary word is, then you're already lost on that question. So this is just a way to remember this word. Kind of funny, okay? Because of what it sounds like. So now, domain. What are we talking about when we're talking about the domain of a function? The x values. Good job. Okay. So when we're given the equation or the graph, the table doesn't matter when we're talking about domains and ranges. Okay? The table is just to help give you points to start your graph and to plot your stuff. If there is no information, like from a word problem or something, that gives you any boundaries, okay, then you are looking at what the graph looks like in the equation. So for my domain, for my x values, can I keep plugging in smaller and smaller x values? Yes, I can. Can I keep plugging in bigger and bigger x values? Yes.
No.
So what's my domain going to be?
2, -2. Wait, it's all those, right?
Nope. Because I just said we're going to ignore the table when we're given the equation or the graph. Okay. So do I have any lowest amount that I can put in for my x?
No.
No. Do I have a highest amount that I'm limited to put in for my x?
Yeah.
No.
Yes.
No.
No.
There's no limitation on my x's, which means my x's are an element of all real numbers. Okay? So this is just another way to write all real numbers. Okay? It's another notation that you need to be aware of for the STAR test. Sometimes it writes all real numbers. Sometimes it writes it like this. We don't write from negative infinity to positive infinity until algebra 2. Okay, so you need to know all real numbers. So what's the range talking about then?
The one that you see the most.
The y values. Okay.
We had a song about that last year.
Okay. Well, we're not talking about the statistics range. We're talking about, which technically is the statistic range is the difference from your highest and your lowest. Okay. You're still looking at your highest and your lowest range values here, but it's your y values that are highest and lowest. So what's my lowest y value?
1.
What's it getting closest and closest to, but never going to cross?
0 and 1.
The 0 right here. Nope, it crossed 0, 1, but right here is my asymptote. So 0 is less than y. It's not less than or equal to because y will never equal 0. It's just going to get closer and closer and closer. Okay? So 0 is less than y. Do I have a high number that y is going to stop at?
No.
No. So it goes on forever. So I don't have anything on the large side of that. So I would say to positive infinity. But we don't use infinities here. So we don't write anything on that side. There's nothing stopping it. So the only thing I'm going to do is rewrite it so that I list my variable first. So y is greater than 0. Meaning that all my y values have to be greater than 0. None of them will be 0 or below 0. Now we're going to watch a fun little video here.
How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1/1000th of a centimeter in thickness. That is 10 to the power of minus 3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of the newspaper. Now, we begin to fold it in half. How many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2/1000ths of a centimeter in thickness. If we fold it in half once again, the paper would become 4/1000ths of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again, always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1024 thousandths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper, we can go very far, but very fast too. Summarizing, if we fold a paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then starting with a piece of Bible paper and folding it 45 times, we get to the Moon. And if we double it one more time, we get back to Earth.
you're right. It is physically impossible to fold a paper normally. Okay, it's physically impossible to fold a paper more than 7 times.
7?
Now, world records have been broke by folding it 8 times, I believe, but it took heavy machinery and a really large piece of paper to do it. And they got it only folded 1 more time. Okay, so you can test that theory later. Okay, but right now, we've just got one more thing that we need to talk about before we're done with our notes for the day. Okay, so graph those 4 equations on your calculator. It can be in Desmos, it can be on your calculator. Okay. Actually, because we're running low on time, I'm just going to pull up my one that I did here on the calculator. Okay. So notice that my black and pink one, okay, start up high and go down. And my blue and red one start down low and go up. Okay, so what do you notice about my pink and black lines?
But they're a little bit farther away.
They are. What do you notice about the equations, though, of those 2 lines?
That one, they're both fractions.
They're both fractions, right? So the pink and the black line are both fraction bases, so they start up high and they go down low. What about my red and blue line? What do you notice about their bases? They're both whole numbers. Okay. So on your notes there, okay, on your notes there, it asks you at the top, okay, what do they have in common? Well, we noticed that they all increased on one side and decreased on the other. The other thing they have in common is that they all passed through the point 0, 1, and they all leveled out, which means they all had horizontal asymptotes. Okay, then on the other side, it asks what's the differences between the graphs. Preston, are you getting these notes so you'll have them?
Yes, actually.
Okay. So on the other side, it says what's different about them. Well, these are the things that we talked about, right? Some of the graphs are decreasing, which means they start up high and they go down. Okay. Some of them are increasing, meaning that they start low and go up. Okay. So remember, we always read our graph from left to right. So if it's increasing, it starts down low and goes up as you read across the page. So as you read across the page, it goes up. If it's decreasing as you read across the page, it would start up high and be going down. The other thing that we noticed and talked about is that those that are increasing have a whole number base. Those that are decreasing have a fraction base. Their base falls between 0 and 1. So at the top of the next page, okay, you need to know this information right here, this blank for some of your get more math points, or just in case I'm not sure if there's one on there asking that, but your initial amount or your starting amount is any number that's multiplied by the base that has the exponent on it. So not the number with the exponent on it. That tells you how it's growing or decreasing. But if there's another number out front, then that's the initial amount. This is your y-intercept. So on all of our example problems, there was a 1 there because it was invisible right in front of our problem. So that's why they all went through the 0.01. Okay. So we're done with the notes part. This section right here needs to be done over the, whoops. This next section right here needs to be finished to see how well you can identify linear, quadratic, or exponential functions over the weekend. And then you do get more math problems. So today, yes, you do have to get more math assignment. It's just domain and range, asymptote, and like I said, maybe identifying the initial value, which is your y-intercepts from graphs. Okay? 7 points today. Yep.